In the last class, we looked at Wisdom Bridge, which we showed with 4 resistors. And you will agree with me that the diagrams we have there is as good as something like this. Okay. This is still Western Bridge. We can say P. Let me look at the labeling again. PRQX. RX and PQ. Yeah, exact. Yeah, this diagram looks exactly like the ones you look all through, because it just occurred to me that it's not until it stays in that shape that you view it as. So this is a galvanometer, which we can draw using an arrow. So if you look at them again, we have resistors P and Q appearing to be. Now let's look at this diagram, forgetting about that galvanometer. Delete that galvanometer, and you see that P and Q are in series, R and X are in series, PQ, which is in series, and RX in series, are in parallel with each other. So the midpoint between PQ and RX is what we are trying to check. So when the voltage at this point, is equal to the voltage at this point between R and X, then the galvanometer will not deflect. Then current will not flow through the galvanometer because they have the same potential. And when they have the same potential, we should not expect current to flow. When you have water in 2 tanks, if you have water in 2 tanks and the water is filled to the same height, if you connect the 2 tanks with a pipe, we should not expect water to flow from one tank to the other because they have the same height, same pressure, different ways you want to define it. You will not expect water to flow in between the 2 tanks because they have the same potential. So the same thing applies in electricity. For current to flow, there should be a difference in potential. So we attempted to calculate what would have the potentials at this point, and we ended up with a summary that says that when the Wisdom Bridge is balanced, then Px will be equal to Qr, right? Px will be equal to Qr, yes. So now, if you look at this meter bridge carefully, you will see in there the Wisdom Bridge. You would notice that we have 2 resistors here, P and Q. And you will also notice that we have something that looks like a resistor here, R and X. If you look at it closely, then that should now take us back to one of the fundamentals of electricity, or let me say resistance, or better still, resistivity. The resistance of a wire depends on the nature of that wire. If it is copper, if it is aluminum, gold, if it is glass, plastic, the resistance of that particular material depends on its nature. That is what. And not just the nature, it also depends on the dimensions, the physical dimensions of that material. When you have two wires, both made of copper, having cylindrical in nature, having the same cross-sectional area, the resistance of a shorter wire is smaller than that of a longer wire. So we can say that the resistance increases with length. If we say that the resistance increases with length, then listen, we can just write it in the language we understand. Resistance R is directly proportional to length. So that's that. There is also another physical dimension, which is the cross-sectional area. The fatter the wire, the lower the resistance. So the resistance of a wire is inversely proportional to the cross-sectional area. What that means is that when you have two wires made up of the same material, for example, copper, the two wires have the same length, but it's one of them is thin, the other is fat. The fatter one will permit easier current flow, while the thinner one would limit current flow compared to the fatter one. Hence, it's easy for us to say that the resistance of a wire will increase when the area decreases. So I think it makes sense to think about resistor as something that limits current flow. When you are traveling and you get to a pothole, when you have a series of potholes ahead of you, those potholes are in series. They will add up to the resistance of the free flow of vehicles moving through. And that constriction would begin to make more vehicles to accumulate at that point where the road is bad. But when you get to a bad portion of the road in which like 3 cars can maneuver themselves to pass through 3 different potholes at a time, then it's easier than having those 3 potholes ahead of each other. So you can say those potholes are in series or in parallel. So when we talk about resistors, electricity, you can relate them to things you are familiar with. So if you think about water flow in a pipe, and there is now a blockage in that pipe, if the blockage is long, you would expect the water flow to reduce. But if it's a short blockage, it's the limitation for free flow of water would reduce. So you can try to picture it because we cannot see the electrons, but at least you can see water. At least. So knowing how to things we are familiar with helps us to picture what we are not really familiar with. And also in physics, we do, or let me say in science, we do so many approximations. If I tell you some of the things we have learned in class that we have both discussed and agreed that some of them are not totally correct, but at least we agreed. When you were in primary school, you were taught that 5 minus 3 is equal to 2. But 3 minus 5 is impossible. When you got to a stage, you told you it's possible that there is something called minus 2. Did the first teacher like? Later they said you cannot find the square root of 3. You can only find that of 4 and 9. Later they said there is decimal number. Later they said you cannot find the square root of a negative number. Later they came with imaginary number. So there are some things we learn. We try to approximate so that we'll be able to understand on a broader level. But when it comes to practical, as time goes on, those that are physics people and those that would love to become, to join the physics party, will begin to see that, oh, some of these things were just to make us understand. And if you don't understand the lie, for you to understand the truth, it will be very difficult. So, coming back to the Western Bridge, we have spoken about a resistor that looks like this, another resistor that looks like this, and now in parallel with another resistor that looks like this. And this resistor at the base is a type of resistor in which you can move all through from this edge to this edge. What that means is that if I say the whole of the resistance of this wire, of this printed resistor, I will say resistor. Like I've said in the past, resistor can be your bulb, can be your fan, it can be your cooker, it can be something that performs work that converts electricity to something useful for you in some other places. So this particular material, if let's assume it is 100 ohms, let's assume this particular resistor, and to make our lives a bit easier, we have said the length of a wire depends on the resistance, that the resistance of a wire depends on its length. Let's now take this to be the length, a particular wire having a certain length L. The resistance from this point to this point, if it is 100 ohms, the resistance from this point to this point will be what? 50, thank you. So the longer you move within this particular material, the larger the resistance that you would have to overcome. So I can come here and just tap here and say that this is like 1/3, this is 30 ohms. I can come here, tap some other, say this is 40, that is from the end points here to here is 40 ohms. And I can come to say, to take another 30% of that wire to say here to here is another 30 ohms. So what this is telling us is that I can take this resistor to be, it can serve as a variable resistor to me, in which I can decide to pick my desired length to say that I have chosen my required resistance. So if I now bring in my galvanometer, sorry, let's give it battery so that it will not feel cheated. Let's give it battery so that it's looking more like a whisking picture. So I can come here, bring in a galvanometer, and the other end of the galvanometer, I can slide it all through this resistor. So as I'm sliding it from the left-hand side to the right-hand side, I can vary the potential that will connect to the other end of this galvanometer. When I take this particular point, that is this point, and I connect it at this edge, it's easy to say that, okay, sorry, before we go that way, let's say that since we have PQ and RX, let's call this our P, let's call this Q, and let's call the left-hand side to be R, and the right-hand side to be X. So there is a particular point on this red resistor, this large resistor Rx. There is a particular point on that resistor in which the potential will be equal to the potential between P and Q. So P and Q are resistors. They have values and connected across a battery. Easily we can determine what is the potential between P and Q. That is, what is the potential at this point? When we begin to slide the other end of this galvanometer all through this wire, all through this resistor, we would expect the voltage at this particular point to vary. At the times, whenever we place this wire at a point where its potential is less than the potential between P and Q, we would expect current to flow from the top through the galvanometer to the bottom. When we slide this to the when we slide it to a particular point where the potential at the top is less than the potential where we have placed the wire at the bottom, we will expect current to flow from the bottom to the top. But there is a particular point on this wire where when we place it, there will be no need for current to flow in either way. That particular point is the balance point. That particular point will have the potential that is equal to the potential between P and Q. So when we fix this wire at that point, we can say the Wheatstone pitch is balanced. So how do we determine R and how do we determine X? How do we determine the value of R and how do we determine the value of X? All we need to do when we are using a meter pitch is to use this first expression, that is resistance of the wire is directly proportional to the length of the wire. I don't know if you still use hot plate in the hostel. Okay, anyway, I noticed that some guys started with yes, they now change to no. But I've identified one or two that I will ask the porters to come and check your rooms. So I wish I can just put a slide here. Okay, let's think about that your hot plate. Now nobody is saying no, we don't have hot plates. Okay. Your hot plates, it's you see series of wires running around like a string, running around, now going to the outlets, right? Right? Somebody said yes then. Okay. Now I have like 4 suspects. So for your gains to get hooked, current must flow through those spring. It will flow through that spring, that coil spring, out. When there is a breakage in those springs, current will be unable to flow. But what we should bring out here is that this particular spring has a certain resistance. And when you power it up, you have connected this to one leg of the power supply, which is, let's say, 220 volts, and the other leg to the neutral, which is 0 volts. Then I can tell you that as you move in this direction, from 0, the potential at those points on the spring will begin to increase from 0, 1, 2, 3, 3.4, 0.5, up to 220. If you are tired of cooking beans, you can just try and, if you have a multimeter, you can just read it. It's straightforward. You see that the potential when you connect one leg of your meter to this point, 0, and you begin to take the other leg all through this wire, the potential, you can do that before it gets hot, the potential at those points will continue to increase until you get to 220. And if you don't want to connect it to 220 volts to reduce risk of electrocution, if you connect it to a 12 volts battery and you take your meter all along, it will move from 0 to 12. So what that is telling us is that at different points, we have different potentials. And at different points, we have different resistance. And how do we determine this resistance? By saying the resistance of the wire is directly proportional to the length of the wire. So when you must have noticed, if you are cooking and somehow that spring gets hot, a normal thing to do is to disconnect the hot plates and reconnect that spring, right? So when you reconnect, another suspect has responded. When you reconnect, you will notice that when you reconnect, there are times in which that spring will get broken. You will take the broken part out and reconnect. When you reconnect, you see that the hot plate will get brighter. It will boil your water faster. The reason is because you have reduced the length of the wire, you have reduced the resistance, more current will flow. Then when more current flows, it will get hot earlier. So when you are in the kitchen, you apply physics. Even if you are using the gas cooker, you apply physics. When you are, for instance, let's go to heat and thermodynamics, you are cooking your rice. Because you are hungry, you now increase the amount of gas. It's still boiling. It's boiling, the temperature will not increase. No matter how you are hungry, you increase it. You have not increased the rate of your cooking. You have only increased the rates of vaporization of your water. So one of the places where I enjoy physics the most is in the kitchen. And as the food goes through the alimentary canal, it's physics. When you swallow the amala with the friction, the lubrication on your esophagus is different from if it's with vegetable. Those that are passing are in trouble this morning. I will make you so hungry. Okay, let's come back to physics of electricity. And though we cannot talk about electricity and stay away from the kitchen anyway, but let's come back and strike some balances. So in this point, if I say that RA divided by RAC, yeah, which is the resistance between this wire A. Okay, sorry, let's come back to, let's look at it like a Whiston bridge. This is P, this is Q. Let's say this is R. And let's say this part is X. Now, a galvanometer has been moved around to get the balance point. By determining that balance point, it means that current will not flow through the galvanometer, And when we say R over X, we don't know R, we don't know X, we have just used a wire. I'm sure you have seen the meter bridge in the laboratory. Okay, if you have not seen the meter bridge, just imagine a wire, a cylindrical wire that runs from A to B. And because it is meter bridge, the length of that wire is 1 meter. 1 meter is 100 centimeters. So when we know that the length is 100 centimeters, we don't even have idea of the thickness of the wire, the resistance of the wire. But what we know is that the length of that wire depends on its resistance. Then we can come to say that, well, we say this certain R at the left-hand side over certain X at the left-hand side must add up to the total resistance of this wire, right? So if I pick this particular point C, I can say that RAC and this particular point C to B plus RCB should add up, give me a resistance that will be the resistance from A to B. So when I know that, then easily I can say that R over X should be equal to L1 over L2. R1 over R2, they would divide themselves, and at the end you would have a unitless factor. The same thing with L1 over L2. They are of the same units. Centimeter will cancel centimeter, or meter will cancel meter, and it will give unitless constant. Since we know that resistance is directly proportional to length, then we can even go to this primary school mathematics that says that R is directly proportional to L. Then we say that R is equal to KL, right? Then we say K is equal to R over L, right? Then we say R1 over L1 is equal to R2 over L2. Then if you play with it a little more, you have R1 over R2 equal to L1 over L2. So any way you twist it, science is your friend. So now let's come back to this. Then it's easy for us to say that L1 plus L2 is 100 centimeters. We know that, right? L1 is the length from point A, while L2 from between point A and C, while L2 is between point C and B. So L1 plus L2 will give us 100 centimeters. So when you take your galvanometer, when you slide it through that wire, you get to a certain point where the bridge is balanced. You get to a certain point where the galvanometer will neither deflect to the right nor to the left, to show you that that point in the wire has a potential that is equal to the potential between P and Q. So this is resistor P, Q. Everything other than P and Q, they are very good conductors with negligible resistance. So let's move forward. So I think we have to conclude it. So then we should say that easily we can say, we've said before that Px is equal to QR. Then from this point, we can come to say that P over Q is equal to R over X. Then since we have established that R over X is equal to L1 over L2, then we can say P over Q. Where else to write now? P over Q is equal to L1 over L2, right? Then since we know that L1 plus L2 is equal to 100 centimeters, then easily we can still come to say that P over Q is equal to L1 over 100 minus L1. Because L2 is L1 plus L2 is 100. Then 100 minus L1 is L2. So what that means is that at a particular point L, at a particular point L1, that gives me the balance point, it can help me to determine the resistance of either P or Q. So in this scenario, if I do not know the resistance of either P or Q, let's say I get the particular value of the resistor P, but I don't know the value of resistor Q, I can set them up on a meter bridge, determine the length of the balance point. On determining the length of the balance point, then I can come to this expression to say that P over Q, known over unknown, equal to L1 over 100 minus L1. So that's straightforward. Or can any mathematician show us any loophole in this expression? Silence means consent. Then we'll move forward. So let's look at potentiometer and its applications. When we talk about potentiometers, we'll run through it quickly because I've taken my time to talk about the meter bridge, and it takes its roots from there. So a potentiometer is an instrument for measuring potential or voltage in a circuit. And it's very popular before the invention of blah, blah, blah. So let's move to business. When we have two resistors, R1 and R2, connected across a battery of voltage, let's say V in, we have seen over and over that when we have a scenario like this, where we have a battery, the diagram I've just shown you is just like we have a battery. Let's give it a value. Because when we say PX, some people just get lost that they've started. So let's say this is also 2 ohms, and this is 4 ohms. The total resistance is what? And the current flow will be what? I had 2 ohms. Okay. The total resistance is what? And since the total resistance is 6, the current flow will be what? Thank you. So current 2 amperes will flow out of this battery, flow to the 2 ohm resistor, through the 4 ohm resistor. So what will be the voltage drop across the 4 ohm resistor? 8 volts. Thank you. So what that is telling us is that when you have your voltmeter, well, we'll say, let's say this is your voltmeter. You connect one leg here. You connect the other leg, or you connect the other leg here. What do you measure? What should you measure on the voltmeter? 0. You measure 0. What will you measure when you connect it here? Yes, 8 volts. Thank you. So what will you measure when you connect it here? 12 volts. Thank you. So that means that we can say that the potential at this point is 8 volts, and potential at this point is 12 volts. So easily, so this point can be set to the 0. So what is the potential difference across the 4 ohm resistor? It's easy to say that 8 minus 0. is it to say that 8 minus 0 to give us 8 as a potential difference across the 4 ohm resistor? And what's the potential difference across 2 ohm resistor? And that is 12, which is connected to the positive terminal of the battery, minus 8 volts. So when you say the potential difference of each of these resistors divided by their resistance, you should still get our I, the 2 amperes. So let's move forward. So what we can determine or deduce from this is that if I have a 12 volts battery, a 4 ohm resistor, and a 2 ohm resistor, but I need 8 volt supply, then I can connect the resistors in this manner and bring out 8 volts, right? If I need 8 volts, but I don't have 8 volts battery, but I have a 12 volts battery. Now I have a 4 ohm resistor and a 2 ohm resistor. I can connect them and tap 8 volts from this point, and it will be 8 volts supply. If I need 4 volts, I can tap out from this point, as which is 12, another point from this point, and it will be 4 volts supply. So what this is has done is that it has divided the voltage, and for that reason, it's called voltage divider. It has divided the voltage, the 12 volts, into 8 and 4. So there are simple ways of going about this without even calculating the current. You can say 4 divided by 2 plus 4 times 12. That will give you 8, right? So what we have is just like what I've just shown you. We have a resistor and another resistor connected to a battery. This is like a 12 volts battery. And the output here is like 8 volts we had. So this is like an input voltage and an output voltage. So a potentiometer can be used to give us fraction of a certain voltage. And so in this place, it's a voltage divider, because the 2 resistors in series have divided the voltage. Okay. So when all the stories here are exactly what I've said about the 12 volts battery, the 2 ohm resistor, and the 4 ohms resistor. So when you determine the current that flows out of the battery, you can easily come to say that V out, relationship between V out and V in, will be this R2 divided by the total resistance times V in will give us V out. And how did we get there? We started by saying what is the current flow. From determining the current flow and the potential drop across each of them, it's easy to say that this is our V out. So when you follow this, it says it all. The current I flows through R1 and R2, and the same current I flows through R2. So, and that led us to saying that I is equal to V in, because it's the potential across R1 and R2 is V in, and it also V in divided by R1 plus R2 is the current I that flows, and V out, which is the potential across R2, is divided by R2, which gives us that same I. So we've said that while using this circuit. So let's move forward. So now imagine that we don't have 2 resistors in this point, but we have a wire that we can slide through. We have something like the meter bridge. We have something like the volume control of our Aboki relay. You can have unlimited amount of resistance. You can tune the volume of your radio to a desired volume level that you desire. What you are doing there is that you are varying a certain resistance by varying that resistance, you are adjusting the out. So just like we said, or taking this to be the hot plate connected to the power supply, and we have agreed that the voltage would increase 0, 1, 2, 3, up to 20. It is connected to 12 volts battery, 0 up to 12. At different points on that hot plate, we have different voltages. So we can actually bring out whatever voltage we need. So when we take this to be a certain wire, let's say to be consistent, let's think about the meter bridge again. 100 centimeter long wire. When this is a 100 centimeter long wire, we can imagine the resistance increasing from the 0 point to the maximum point. When we connect that 100 centimeter wire across a 100 volt socket, then you would agree with me that when you get to 1 centimeter, it should be 1 volt. And you get to 2 centimeters, it should be 2 volts. So that means that from that wire, you can derive whatsoever voltage you desire from 0, the minimum, to 100, the maximum, right? Right? Okay, so let's move on. Is anyone saying no? Any objection? Any counter motion? So this is an example. R1 is 1 ohm, R2 is 3 ohms. Then what is the PD across R1 and R2? So let's quickly do that. R1 is 1 ohm, right? 1 ohm. Oh. And R2 is 3 ohm. What is the PD across R1 and R2? The potential difference across R2 should be R2, which should be V out, should be equal to now you want to take us back to the kitchen, but your temptation has flopped. So we can say V out is R2 over R1 plus R2 times V in. Times V in. V out is R2 over R1 plus R2 times V in. So that's the potential difference across R2. And what is potential difference across R1? We don't need a prophet to tell us that the potential difference across R1 is V in minus V out, right? Because from this point to this point is V in, halfway downwards is V out, then that halfway upward should be the remaining, should be V in minus V out. True or false? So this can also be applied to determine the EMF of a cell. When you have a cell of EMF E naught, that EMF E naught is a cell or a battery with known EMF. You know the EMF of that battery. And you have a certain length of wire, let's say 1 meter, 100 centimeters for simplicity. Now you now have another battery, EX. You don't know the potential, the EMF of that battery. But you can connect, but you are sure that, or you assume, not even sure, you assume that the EMF EX is less than E naught. Then what you can do is to connect a galvanometer in this manner, and you begin to slide. Like forgetting about this galvanometer and EX, we've established the fact that the potential difference will cut across the length of the wire, and we can determine different resistances by different lengths, to say different potentials by touching different lengths. Then when you begin to slide this galvanometer, this jockey around the meter, the length of that wire, when you slide it to a particular point where the potential difference between point A and that particular point X, when the potential at that point is less than EX, we'll expect current to flow out of EX. When you slide it to a particular point where EX is now less than E naught, sorry, at the particular point where the potential at that point is now greater than EX, we expect current to flow into that battery. But there will still be one particular point of balance where current will neither flow in nor flow out of EX. At that particular point, we can say that point has the same potential EX, like the EMF of the battery X. So when we take this particular length L, to say that the length L here has a potential that's equal to the EMF of battery EX, then the question will now be, what is still that EMF? And the simple answer is to say that from A to B, which we know to be 100 centimeter, has potential difference E naught, right? A to B is connected to battery E naught. So A to B has potential difference E naught. So A to B, AB has potential difference E naught. Then A to X, and not just potential difference E naught, it has length 100 centimeter. Then we also have length AX, which is the balance point, having EMF EX and having a certain length L. Then easily we can say that that EX will be equal to this length L divided by 100 centimeter, which is the total length of wire, equal to EX, the EMF of the unknown battery, divided by E naught. So what that's telling us is that this particular length L has just told us that I correspond to EMF EX. While this particular length AB has told us that I correspond to EMF E naught. Then this midway, as the length increases, resistance increases, potential drop also increases. For that reason, it's easy for us to say that the length AX divided by the length AB, which is L divided by 100, is equal to EMF EX divided by EMF E naught. If you don't get it now, don't worry. When you have eaten again, you'll get it. One of my rules of physics is that I don't go to physics class with an empty stomach, because it drains. The brain will be taking more energy, chemical energy, from the EBA. And I don't take salt, because salt brings smaller power. So just like this and like this, It's all saying the same thing, the same thing. So I'll make sure I get this online today. And apologies for the late upload. So there's an example here which you can play with. And when you have other questions, please feel free to send me an email. Over the week has been so busy. I was responding to one email yesterday and